Okay, welcome back to the afternoon session. Our first speaker today is Guanyu Zhu. He's going to tell us about universal logical gate sets with constant depth circuits for topological and hyperbolic quantum codes.
Thanks, Steve, for the introduction. So this work was done when I was back in Maryland with Lee Lavasani and Mason Bakshili. So the corresponding papers are listed here. So let me begin with introducing the quantum error correcting codes, which can be captured by 3 parameters, where n are the total physical qubits number, which redundantly encode k logical qubits. The encoding rate is defined to be k over n, while the inverse is the space overhead. So the logical space is a subspace of the full Hilbert space, and specified by syndrome operator Si to take the eigenvalue plus 1. The codistance d is the weight of the smallest operator that connects different logical states. So now let's talk about the logical gates on the encoded qubits. So a very well-known class of logical gates are the so-called transversal gates acting on an individual subsystem under transversal partition. A well-known example is the transversal CNOS between 2 CSS codes. So it has the advantage that it has no time overhead, and it also does not spread errors. However, there's a well-known Easton-Keneal no-go theorem that says that transversal gates alone cannot be universal. Hence, a long-standing question is that what's the most harmless modification of a transversal condition that allows a universal logical gate set? Previous schemes to achieve this and circumvent the no-go theorem include code switching, magic state distillation, and also braiding of non-abelian aliens in non-abelian topological codes. So all of these schemes include either measurements or a unitary circuits, which the depth grows linearly in distance d. And all of them have some significant space-time overhead. So we are interested in the question that what are the ultimate space-time overhead costs for quantum memory and also quantum computation. So in this talk, our main results is braids and dentures in general topological codes can always be performed by constant depth unitary circuits, which implies universal protected logical gate set with constant depth unitary circuit is possible. And when I apply these methods to hyperbolic codes, we can also preserve the constant space overhead of the quantum memory. So we focus on a class of codes which are topological codes. They are based on topological order states of matter, which are described by topological quantum field theory, abbreviated as TQFT. The TQFT assigns a Hilbert space H and which is the code space H sigma to a surface sigma. So the recipe to turn it into a quantum code is to pick up a triangulation lambda of the surface and put qubits on edges. So let's be more concrete. So in this talk, I will focus on the class of code called Turari-Vero codes. They originate from the Turari-Vero topological quantum field theory and was introduced to the quantum information community by this paper. So the code is defined on a triangulation where the qubit sets on the edge. One can also define the dual trivalent graph. And and hence can write down a so-called Levin-1 Hamiltonians on this trivalent graph. So the Levin-1 Hamiltonians is a permanent model for all non-chiral topological orders in 2D, including the special example as toric code. So this model can be considered as a generalization of toric code in the sense that it also has the vertex and the placate syndrome operators. So the ground states of this Hamiltonian is a string net condensation. So to illustrate this, I show a string net here where the occupied edge by a string corresponds to a qubit in the 1 state, and the unoccupied side has qubit in the 0 state. So this is more general than the usual torical case in the sense that the string can bifurcate. That's included in the so-called fusion rules and imposed by the vertex operator. So using Fibonacci alien as an example, 2 Fibonacci alien can fuse into either vacuum or +1. So that corresponds to on a vertex, either 2 of the edge are occupied or 3 of them are occupied. So if it satisfies the fusion rule, it has eigenvalue +1. Otherwise, it has eigenvalue 0, so which induce energy penalty. Similar to the torical case, one can also define the plaqué terms, which flips the string configurations to create a condensate of these string nets. So in this context, this plaqué term is a 12-body syndrome operator, which can in turn be expressed as a product of so-called F symbols, and then they are part of the defining data of topological codes, so they are different for different types of topological codes. There are ongoing work on the error correction and the decoding process on this type of, on the non-abelian Torari code, including Fibonacci. So the essence of doing topological quantum computation with Torari code is essentially a retriangulated surface. So here the elementary move is so-called 2-2 Parkner moves. So it flips the central edge between two triangles. It maps two faces to other faces. So it's called 2-2 Parkner moves. On the dual trivalent graph, it's also called F move, which deforms the trivalent graph in such a way. And in this picture, it directly corresponds to the unitary transformation of TQFT wave functions defined on different trivalent graphs, which are essentially a superposition of the string nets I showed in the last slide. So here F is just F symbols. Since it's a unitary transformation, so one can always write down a unitary circuit for this F move. So in the context of Fibonacci code, it's just a controlled unitary where the control qubits are the 4 qubits on the edge. So this circuit was written down by Bonstein and De Vincenzo. So another type of move is so-called 1-3 Parkner move. So it essentially entangle the 3 ancillar qubits, these white dots, into the code space, and add a vertex in the middle of the triangle. In the dual graph picture, it adds a triangular loop in the center of the vertex. So when going from left to right, it adds qubits and hence fine-grain the lattice. So if the reverse way is corresponds to a coarse-graining process, which removes qubits out of the subspace. It also relates to the unitary transformation of the TQFT wave function, and it can also be implemented as a unitary circuit. So now we come to how to apply logical gates on topological codes from a TQFT language. So in this language, the logical gates are just a surface deformation. So mathematically speaking, it's called diffeomorphism on a surface. So in particular, it's a self-diffeomorphism which maps the surface back to itself. And the TQFT associates a protected logical unitary on the code subspace, which also maps the subspace back to itself. A well-known example is the braiding of punctures on a surface. So from this, you can see that the surface is exactly mapped back to itself, although there's a non-trivial process happens, which can be indicated by the string attached to the punctures. So now let me introduce a mathematical concept called mapping class group of surface sigma, so which is a group of all these self-diffeomorphisms modulo some local diffeomorphism which can be continuously connected to the identity map. So it's also called a large diffeomorphism. So a special case is the mapping class group of a disk with n punctures. So in this case, so it's exactly equivalent to a braid group of n strands, and that's the usual picture of topological quantum computation, where one adiabatically braid the non-abelian aliens, which takes time of order the codistance d, where d here is basically the separation of the punctures. One can also consider a more general case, define mapping class group on a surface with n punctures and the genus G. So this mapping class group is generated by the braiding of neighboring punctures and also 3G minus 1 dentwists along the 3 types of cycles indicated by different colors here. So the definition of a dentwist around a cycle is just to cut the handle on this particular cycle, twist by 2 pi and glue back together such that it twisted the logical operators. So our main result is that braids and dentwists can be implemented by 2 processes. One is a local constant depth circuit denoted by LU. The other is a permutation of qubits where the representation is denoted by P sigma. So we consider n data qubits and the NA ancillar qubits. So the mapping class group element acting on the data qubits in the codes, it can actually be implemented with these 2 operators acting on the product states of the data qubits and the ancillar qubits. So furthermore, if we allow long-range swaps, any permutation can be also done by a constant depth circuit, which can be understood that you can decompose any permutation as a product of cyclic permutations, which can in turn be performed by two reflections corresponding to a depth two circuit of parallel swaps. In some, braids and dentist will correspond to a constant depth unitary circuit. So when applying this result to a Fibonacci derivative code, we can achieve a universal gate set for quantum computation. So there are two methods to achieve this protocol. So one is the instant braiding. So in this way, so instead of the usual way where we treat aliens as objects in the space and adiabatically moving them, here we fix the objects but stretch the space between this stretch or squeeze the space between the objects. So which can be understood with the entanglement renormalization or so-called mirror picture, where you can separate the two neighboring punctures to distance d in logarithmic d steps. Actually, for the quantum computation purpose, we can do this less violently in the sense that because the punctures here has to be away at least in an order of codistance. So we only need to change them by a constant factor. So if I want to change it by a factor of 2, I can just apply one step of local entanglement realization to stretch the surface in between and squeeze the surface on the other two sides. So it's always a constant depth circuit. So one way to understanding this is that mirror is like an expanding universe. So in an expanding universe, the expanding rate is independent of the distance between two objects. So they can be changed by a factor of 2 whenever, for if they are 1 kilometers away or they are 1 light years away, it's the same time to change it by a factor of 2. So to illustrate we illustrate this with a concrete protocol of braiding two punctures with codistance d apart on a triangulation. So here is the dual graph, which is a trivalent graph. So we can do one step of Parkner moves to coarse grain the region on top and fine grain the region on the bottom. So in this case, we can just apply one step of qubit permutation such that the aliens is just instantaneously move to above in a codistance d. So in sum, independent of codistance d, we can always achieve the full braiding process in finite number of steps. In this example, it's just 6 steps. So the essence of the first method is the local geometry deformation of the surface. So now there's a second method which exploits the fact that dentist and braid are just some non-trivial maps on the surface. So we want to implement a particular larger diffeomorphism represent the element of a mapping class group. Can be done in 2 steps. First step is to move the vertices lambda according to the map FU, and while preserving the connectivity of the graph. So this will give us a new triangulation lambda prime. So the second, and it can be implemented with a permutation of physical qubits. So the step 2 is to retriangulate the surface back to itself such that back to the original Hilbert space. So as an illustration, we consider doing this on a torus, where we represent torus by a square patch with periodic boundary condition where the opposite sides are identified. So we can apply a shear map to permute the vertices and edges upward, so in one step. And so because of the periodic boundary condition, it's equivalent to the same surface where the horizontal loop beta is mapped to the twisted loop beta alpha. That's exactly a dentist. The only thing we need to do is to retriangulate back to itself. So that's just one step of two Parkner moves on each of the 2 triangles in parallel. So now we can apply this method also to the hyperbolic codes to preserve a constant space overhead. So to understand that, the constant space overhead is just due to the profound Gauss-Bonnet theorem, which relates the local geometry property, the curvature, to the global topological property, the Euler characteristic, which can be expressed as a function of the genus G. So with constant hyperbolic connective curvature, so this formula just becomes the area is proportional to the genus G. So in topological code, genus G is just the number of logical qubits, and the area is proportional to physical qubits. So we achieve a constant encoding rate. one can also define the trivial code on the hyperbolic surface with a hyperbolic triangulation. And also there, one can write down the Levin-1 Hamiltonian on the hyperbolic triangle graph, which is the dual graph of this picture. So now we need to obtain a non-zero genus. So to do that, we can, one way is to pick up a hyperbolic 4G gun and glue together every other edge with the same color. So that's equivalent to a high genus G surface, and we illustrate with example G equals 2. One can further tie the whole hyperbolic plane with this 4G gun as a fundamental domain to show the periodic structure, periodic boundary condition. So now we can do similar to the torus case. We can do a shear map to map the region below, so such that the beta loop is again mapped to the twisted loop. So because of the periodic boundary condition, this surface is exactly the original one. It's just a different way to choose the fundamental domain. So that finished the first step of the protocol. So the second step is we can also use a constant depth circuit to retriangulate the surface to obtain the original surface with the same triangulation. So in sum, that we can achieve universal logical gate set with constant depth unitary circuit, also with constant space overhead. Finally, let's talk about the phototorrance property that, so our map only maps a local region R to another local region R prime, where the area is changed by a constant factor independent of the codistance D. So which means any operator is changed to a new operator where the support is only changed by a constant factor. Which is the same for the error string. So the error string is stretched or squeezed by a constant factor such that it remains correctable. So these logical gates are protected. However, to achieve full phototorrance, we should also consider applying multiple of these logical gates and do decoding. So in the worst case, so in log these steps, the error string could grow to the codistance. So with measurement error, to correct that, we need to do d rounds of single measurements and hence decode the error. So I expect that to achieve full phototorrance, we have a time overhead or the d over log d. So we can also compare our result where we have a space overhead or the d over log d to the previous optimal scheme by Gaussman and quantum expander code, where the gates can only be applied sequentially. So for a highly parallel circuit, we might have an advantage. So here is the summary. So finally, I also want to emphasize that for topological quantum computation now, it turns out that not topology is important, but also the geometry. The geometry of the quantum states and the space-time history is related to the complexity of the quantum circuit. So that's all. So thanks for your attention.
Okay, we have plenty of time for questions. So that was a little bit quick for me. Can you maybe go back to the slides where you describe why this is fault tolerant? Because I think the Bear protocol where you're describing these shearing and stretching moves, it seems to me like, let's say you have some thermal anion creep into the system or something, then wouldn't these diffeomorphisms, couldn't they stretch?
Right.
You know, why can't an anion come along for the ride and then create a logical error?
Yeah, to kind of illustrate what's happening, that is that the kind of a map we have is kind of a locality preserving in the sense that it doesn't make it kind of to a disjoint operator, and it only changed the support of the error string by a constant factor. So it's a continuous map, but it also changed the local area only by a constant factor. So there's some region here is mapped to some new region here, but the ratio of the area is always a constant factor, which is independent of codistance d. So it's if you have a small error, much smaller than codistance d, it's still much smaller than codistance d. So you can correct it.
Right, I see. So then the point is that string labeled B gets stretched by this move, but it doesn't stretch far enough. Yeah. So I guess maybe I'm not worried about it. Oh, I see. Because your logical degrees of freedom are always properly topological with respect to the genus of the surface.
Right.
So you're never computing in
corrupted.
an excited state where
Yeah.
you have some pinned any on.
Yeah, that's right. So I mean, I have this appendix that I define as so-called protect logical gates. So it should satisfy two properties. One is that this map preserves the code space, which we have achieved, map back to itself. The second is it should change the support of any operator only by a constant factor. So such that the error is still spread in a controllable way, and you can later make it for torrent by inserting enough rounds of syndrome measurements and error decoding and recovery. So how many rounds you should apply actually depends on the protocol of the particular quantum algorithm, how the error is spread. So in some cases, if we, for example, apply dentist along the same cycle, you will see the error only spreads linearly. So you can apply D rounds of error correction on D gates. But in some very bad case, it could stretch exponentially, because here we don't have a geometric locality, so we don't have the light cone constraint. So it could kind of expand exponentially, so in log beta.
This is the role of the, so I wasn't entirely clear on the role that the permutation played either. So is this coming in?
Yeah, that's because
of
the permutation is long range, so it's not a geometrically local. So I don't have kind of a light cone picture. But still, the operators which kind of join together are mapped to a new kind of operator, which it's still in the same region, kind of it's connected.
But the region doesn't necessarily matter if you're going to do this permutation, right?
If I don't need to do, what do you mean?
Well, you have to do this permutation afterwards to get the logical gate. So
Yeah.
why should it matter if they're locally constrained?
So it might be good for decoding.
Well, I may still have some questions, but I want to see if there's anybody else who has questions first. Okay, we're just going to keep talking for another 20 minutes or so, if that's cool. Now, are there any other questions? We have a question here.
I just have a simple question. So you mentioned that the Turai-Vero, like there's a code, Turai-Vero code, but so is that code a stabilizer code in general, or because if my memory is correct, somehow some operators cannot be written as a stabilizer.
It's so the definition of stabilizers is that the syndrome operators has to be Pauli operators, at least, or maybe even generalized Pauli operators. But for the non-abelian Turai-Vero codes, they are not necessarily Pauli operators. They are more complicated operators.
Yeah. So somehow you can also write something like in the in that double semion model, maybe some -1 to the some sigma power whatever, right?
So
yeah, some phase factor So I'm just wondering whether that can be also
but
measured
in general,
as a syndrome measurement, some syndrome measurement, something like that.
For some simple code, maybe you talk about the double semion code, which is still abelian, and I can write it in the form you just said. But for more like Fibonacci code, I don't know how to write it in a kind of expand in a function of Pauli operator. You can always approximate it with a Pauli operator with maybe some polynomial numbers of operators to approximate it.
So you say that there's always some method to measure the syndrome?
Yeah, there are ongoing works on how to measure this syndrome.
So it's not clear. I mean, maybe there's some example, but there's no general
it's kind
procedure.
of clear to me, but I mean, it's not in the literature yet. I mean, I listed some reference, and there's a dissertation by Bonesteel, and he has said something about how to measure the syndrome. But there are other ways to do that as well.
Maybe I can just add, this might clarify, the ground state of these things is a frustration-free ground state of those local terms. So if you measure all of the plaquette operators and all the vertex operators of that Hamiltonian and you find that they're all zero, that's equivalent to saying that the syndrome was zero. So you can simultaneously measure those operators and find that the ground state will simultaneously satisfy all of those checks.
Yeah,
so it's a stabilizer in that sense that it's a joint +1 eigenspace of a bunch of local operators.
Yeah, it's still a commuting project model. All the syndrome operators commute, so you can measure simultaneously. But it's not Pauli. It's just.
Okay, I think that's all the time we have for questions. Let's thank Guanyu again.